Good morning, friends. We start today one new thing. API 572. Inspection practices for pressure vessel. This recommendation practice RP supplements API 510 by providing pressure vessel inspectors with information that can improve skills and increase basic knowledge of inspection practice. This RP describes inspection practice for the various type of pressure vessels: drums, heat exchangers, columns, reactors, air coolers, spheres used in petroleum refineries and chemical plants. The RP addresses vessel components, inspection planning process, inspection intervals, method of inspection, assessment, method of repair, records and reports. API 510 has requirements and expectations for inspection of pressure vessel. Normative reference 510, 571, 574, 579-1 ASME FFS1 fitness for service, 580 risk-based inspection, API publication 2217A 2217 guideline for safe work in inert confined spaces in the petroleum and petrochemical industry. Alteration, a physical change in any component that has design implications that affect the pressure containing capability of the pressure vessel beyond the scope described in existing data reports. The following should not be considered: alteration, any comparable or duplicate replacement, the addition of any reinforcement nozzle less than or equal to size of existing reinforced nozzles, and the addition of nozzles not requiring reinforcement. Cladding, a metal integrally bonded into another metal under high pressure and temperature, whose properties are better suited to resist damage from the process than the substrate material. CMLs designated areas of pressure vessels where periodic examinations are conducted in order to directly assess the condition of the vessel. CMLs may contain one or more examination points and utilize multiple inspection techniques that are based on the predicted damage mechanisms to give the highest probability of detection. CMLs can be single small area on a pressure vessel, the 2-inch diameter spot, or plane through a section of a nozzle. The recording points exist in all 4 quadrants of the plane. CMLs now include but are not limited to what were previously called TMLs. Corrosion specialty: a person acceptable to the owner user who has knowledge and experience in corrosion damage mechanisms, metallurgy, material selection, and corrosion monitoring techniques. CUI: corrosion under insulation. External corrosion of carbon steel piping, pressure vessels, and structural components resulting from water trapped under insulation. External chloride stress corrosion cracking of austenitic and duplex stainless steel under insulation is also classified as CUI damage. Damage mechanism: any type of damage encountered in the refining and chemical process industry that can result in flaws, defects that can affect the integrity of vessels, corrosion, cracking, erosion, dents, and other mechanical, physical, or chemical impacts. See API RP 571 for a comprehensive list and description of damage mechanism. Damage mode: the physical manifestation of damage. Wall thinning, pitting, cracking, or rupture. Defect: one of the more flaws whose aggregate size, shape, orientation, location, or properties do not meet specified acceptance criteria and are rejectable. Examination point, recording point, measuring point, test point. Test point is a term no longer in use as test refers to mechanical physical test, tensile test, pressure test. An area within a CML defined as a circle having a diameter not greater than 3 inch, 75 mm. For a pressure vessel, CMLs may contain multiple examination points. For example, vessel nozzle may have CML and have multiple examination points. An examination point in 4 quadrants of CML on the nozzle. External inspection, visual inspection performed from the outside of the pressure vessel to find conditions that could impact the vessel's ability to maintain pressure integrity or conditions that compromise the integrity of the supporting structures, ladders, platforms, support. The external inspection may be done either while the vessel is operating or while the vessel is out of service and can be conducted as an on-stream inspection. Flaw, imperfection, or other discontinuities noted during inspections that may or may not exceed the applicable acceptance criteria. In service, designated pressure vessel that has been placed in operation opposed to a new construction prior to being placed in service or retired vessel. Pressure vessel not in operation because of process outage is still considered an in-service pressure vessel. Doesn't include pressure vessels that are still under construction or in transport to site prior to being placed in service, or pressure vessels that have been retired from service. Doesn't include pressure vessels that are temporarily out of service but still in place in an operating site. Stays in the service life of a vessel between the installation and being removed from the service. Lining, a non-metallic and metallic material installed on the interior of a vessel whose properties are better suited to resist damage from the process than the substrate material. Maximum allowable working pressure, MAWP. Maximum gas pressure permitted at the top of the pressure vessel in the operating position for a designated temperature. Pressure is based on calculations using a minimum of average fitted thickness for a critical vessel element, exclusive of thickness designated for corrosion, and adjusted for applicable static head pressure and non-pressure loads, wind, earthquake, etc. The MAWP may refer to either the original design or a retarded MAWP. Minimum design metal temperature. This is maximum gauge pressure. The lowest permissible metal temperature for a given material at a specific thickness based on the resistance to brittle fracture. In the case of minimum allowable MAT, allowable temperature, it may be single temperature or an envelope of allowable operating temperature as function of pressure. It is generally the minimum temperature at which the significant load can be applied to a pressure vessel as defined in the applicable construction code. ASME BPPC Section 8 Division 1 Paragraph UG 20B might also be obtained through FFS evaluation on stream condition whereby pressure vessel has not been prepared for internal inspection. Owner user. An owner user is the pressure vessel who exercises control over the operation, engineering, inspection, repair, alteration, maintenance, pressure testing, and re-rating of those pressure vessels. Pressure design thickness. Minimum wall thickness needed to hold design pressure at design temperature as determined using the rating code formula. Doesn't include thickness for structural loads, corrosion allowance, or mill tolerance. Pressure vessel, a container designed to withstand internal and external pressure. The pressure may be imposed by an external source, by an applicable of heat from direct or indirect source, or by any combination thereof. These definitions include heat exchangers, air coolers, column towers, on-fired steam generators, boilers, and other vapor generating vessels that use heat from the operating of a processing system or other indirect heat source. Pressure vessel engineer, a person acceptable to the owner user who is knowledgeable and experienced in the engineering discipline associated with evaluating mechanical and material characteristics that affect the integrity and reliability of pressure vessels. The pressure vessel engineer, by consulting with appropriate specialists, should be regarded as composite to all entities necessary to properly address the technical requirements. Whenever the term engineer is used in the ERP, it refers to a pressure vessel engineer. Repair, the work necessary to restore a vessel to conditions suitable for safe operation in the design condition. If any of the restorative work result in change to design temperature MDMT, MAWP, the work shall consider an alteration and the requirement for re-rating shall be satisfied. Any welding, cutting or grinding operation on a pressure containing component not specifically considered an alteration is considered a repair. Re-rating, a change in either of the design temperature rating MDMT, MAWP rating of a vessel. The design temperature and MAWP of a vessel may be increased or decreased because of re-rating. De-rating below original design condition is permissible way to provide additional corrosion allowance. Risk-based inspection, RBI. A risk assessment and management process that considers both probability of failure and consequences of failure due to material deterioration, and that is focused on inspection planning for loss of contaminants of pressurizing equipment in processing facilities due to material deterioration. The risks are managed primarily through inspection in order to influence the probability of failure, but can also be managed through various other methods to control the probability and consequences of failure. Strip lining, strips of metal plates or sheets that are welded to the inside of the vessel wall for the purpose of protecting the vessel construction material from interaction with process fluids. Normally, the strips are more corrosion resistance of erosion resistance alloy than vessel wall and provide additional corrosion erosion resistance. This is similar to plate lining, except narrower strips are used instead of larger plates. Temper embrittlement, the reduction of toughness due to metallurgical changes that can occur in some low alloy steels. 2.25 chrome 1 moly, result of long-term exposure in the temperature range of about 650 degrees centigrade, 650 degrees Fahrenheit to 1100 degrees Fahrenheit, that is 345 to 595 degrees centigrade. Testing, within this document, testing generally refers to either pressure testing, whether performed hydrostatically, pneumatically, or combination hydrostatic pneumatic, or mechanical testing to determine such a data as material hardness, strength, notch toughness. Testing, however, doesn't refer to NDE using techniques such as liquid penetrant examination, magnetic particle examination, ultrasonic examination, radiographic examination, etc. So this testing doesn't refer to this. This is NDE, non-destructive examination, as per API. Weld buildup, the use of weld metal and similar composition to the base metal for the purpose of restoring base metal thickness. Weld overlay, the use of weld metal of a composition different than base metal to provide corrosion and erosion resistance to the base metal. Acronyms and abbreviations. AUT, automated ultrasonic examination. CUF, corrosion under fireproofing. ET, eddy current examination. FRI, fractionation research incorporated. FRP, fiber reinforced plastic. H2S, hydrogen sulfide. MT, magnetic particle examination. MOC, management of change. NDE, non-destructive examination. PASCC, polyethylenic acid. Polyethylenic acid, stress corrosion cracking. PRD, pressure relief device. PT, liquid penetrant examination. RT, radiographic examination. UT, ultrasonic examination. WFMT, wet fluorescent magnetic particle examination. Introduction to pressure vessel. General, a pressure vessel is a container designed to withstand internal and external pressure. The pressure vessel may have been constructed in accordance with ASME BPVC Section 8, other recognized pressure vessel codes, or as approved by jurisdiction. These codes typically limit design basis to an external or internal design pressure no less than 15 lb or per inch square, 15 psi or 103 kPa. However, this RP also includes vessels that operate at lower pressures. External pressure on a vessel can caused by internal vacuum or fluid pressure between narrowed jacket and the vessel wall. Vessels subjected to external pressure are usually inspected in the same manner as those subjected in internal pressure. Pressure vessels are designed in various shapes. They may be cylindrical, flat, conical, spherical, semi-elliptic, ellipsoidal, hemispherical heads, spherical, spheroidal boxes with flat rectangular square plate heads, such as those used for headers of air-cooled exchangers or lobed. They may be modular construction. Cylindrical vessels, including exchangers and condensers may be either vertical or horizontal and may be supported by steel columns. Cylindrical plate skirts or plate lugs attached to the cell. Spherical vessels are usually supported by steel columns attached to the cell or by skirt. Methods of construction. Prior to the development of welding, riveting was most common method of construction. Seams were either lapped or riveted, or butted with the butt straps and then riveted. To prevent leakage, the edges of the seams and rivets were caulked. At high temperature, it was difficult to keep the caulking tight. After the technique of welding was developed, a light bead of weld was applied to the caulking edges. Although some vessels of this type can still be found in older refineries, this method of construction is seldom used today. Today, most pressure vessels are constructed with welded joints. Cell rings are usually made by rolling plate and either elevated or ambient temperature. The cylinder is formed by welding the ends of rolled plate together. This yields a cylinder with a longitudinal weld. Hot forging is another method to making cylindrical vessels. Some vessels manufacture hot forged cylindrical cell rings for high pressure heavy wall vessels, such as those used for hydro treater or hydrocracker reactors. This method doesn't produce a longitudinal seam in the cylinder. In a multi-layer method, the cylindrical section is made up of a number of thin concrete cylinders fabricated together, one over the other until the desired thickness is obtained. Multi-layer construction is sometimes used for heavy wall reactors and vessels subjected to high pressure. Materials of construction. Carbon steel is the most common material used to construct pressure vessels. However, wide range of materials are used to construct pressure vessels depending on compatibility with fluid service. Typical examples are austenitic or ferritic alloy 400, nickel, titanium, high nickel alloys, aluminum alloys, copper alloys, except alloy 400 are seldom used in refinery vessels but are common with heat exchanger tubes and may be found in petrochemical plant vessels. Materials used to construct the various parts of heat exchangers are selected to safely handle the service and the heat load required. Materials that will most economically resist the type of corrosion expected are selected. Exchanger cells are usually made up of carbon steel but may be made of corrosion resistance alloy or clad with a corrosion resistance material. Exchanger channels or baffles are made of carbon steel or a suitable corrosion resistance alloy material, usually similar to the material of tubes. Tubes for exchanger bundles may be variety of materials where water is used as a cooling or condensing medium. They are generally made up of copper-based alloys or steel. In water applications where a copper alloys or steels will not provide sufficient corrosion protection, higher alloy materials may be used, such as duplex stainless steel or tube ID may be coated. Baked epoxy or similar titanium may be used to seawater application, where the exchange is between two different hydrocarbons. The tubes may be made up of steel or a suitable corrosion resistance alloy tubes consisting of an inner layer of one material and outer layer of different material bimetallic may in some cases be required to resist two different corrosive medium. Tube set or exchanger bundles are much made of variety of materials where water is the cooling or condensing medium. They are usually made up of Admiralty brass or steel, but may be constructed high alloy steels, clad or solid. Titanium may be used in seawater application where the exchange of heat in between the two hydrocarbons. The tube sheet may be composed of steel or suitable corrosion resistance alloy. In some cases, it may be necessary to face one side of tube sheet with a material different from facing the others resist to different corrosive mediums. If carbon steel would not resist the corrosion and erosion expected or would cause contamination of the product, vessel may be lined with other metals and non-metals. A lined vessel is usually more economical than the built of a solid corrosion resistant material. However, when the pressure vessel is operated at high temperature, a high pressure or both solid alloy may be used, may be both necessary and economical. Metallic liners are installed in various ways. It should be noted that non-integrally bonded metallic liners are not counted as a part of pressure boundary of a pressure vessel. They may be an integral part of the plate material, rolled or explosion bonded before fabrication of the vessel. They may instead be separate sheet of metal fastened to the vessel by welding. Corrosion resistant metal can also be applied to the vessel surface by various weld overlay process. Metallic liners may be made of ferritic alloy, Fe 400, nickel, lead, and any other metal resistant to the corrosive agent. Figure 1 through Figure 4 show various methods of applying metal lining. Figure 5 and Figure 6 show hex mesh installation to support the refractory lining and the reinforced refractory lining. Type 3016 stainless steel clad vessel. Non-metallic liners may be used to resist corrosion and erosion, reduce fouling potential. Exchanger tube or to insulate the reduce the temperature of on the walls of pressure vessel. The most common non-metallic lining material are reinforced concrete, acid brick refractory material, insulating material, carbon brick, block rubber, phenolic epoxy coating, glass and plastic. Pressure vessels constructed out of non-metallic materials are usually made from fiber reinforced plastic and can be more resistant to some corrosive service. FRP can be made with different resins. The matrix material and typically use glass fiber as the reinforcement. Reinforced thermoset plastic are a type of FRP that most rigid due to the use of thermoset resin for the matrix rather than a thermoplastic. Both of these non-metallic materials have varying strength due to the type of fiber used, fiber weave, and the layup of the fiber layer. Internal component and equipment. Many pressure vessels have no internals. Others have internals such as buffers, baffles, distribution piping, trays, mesh, or strip type packing gates, catalyst, bed support, cyclone, pipe coils, spray nozzles, demister pads, and quench lines. Large spheroids may have internal bracing and ties, and most vacuum-rated vessels have either external or internal stiffening rings. Some pressure vessels have heat exchangers or reboilers located in the Lower cell area, or typically internal component of pressure equipment, are not considered part of the pressure containing design of the equipment. Weld metal surfacing. Strip line vessel. Hex mesh installation for refractory line. Reinforced refractory. Cell and tube heat exchangers have internal tube bundles with baffles or support plates which vary with service and heat load the exchanger is designed to handle. Uses of pressure vessels. Pressure vessels are used in most process in a refinery or petrochemical plant. They are used to contain process fluids. A pressure vessel can be used as a thermal reactor or a catalytic reactor to contain the chemical change required by the process as a fractionator to separate various constituent produced in the reaction, as a separator to separate gases, chemicals, or catalyst from a product, as a surge drum for liquids, as a chemical treating unit, as a setting drum to permit separation of chemical from treated product, as a regenerator to restore catalyst or chemical to its original properties, or as a heat exchanger, condenser, cooler, or other type of vessel for any of the various other purposes. Figure 7 through Figure 12 illustrates various types of pressure vessels. Design and construction standard. Vertical heat exchanger, horizontal vessel. So design and construction standards. Prior to early 1930s, most unfired pressure vessels for refineries were built to the design and specification of the user or manufacturer. Later, most pressure vessels in US were built conform either API ASME code for on-fired pressure vessel for petroleum liquids and gases to Section 8 or ASME BPVC. Publications of the API ASME code for unfired pressure vessel for petroleum liquids and gases were discontinued as of December 31, 1956 and is no longer used for new vessels. Section 8 of the ASME PVC is divided into three parts: Division 1, Division 2, Division 3, Section 8. Division 1 provides requirement of application to the design, fabrication, inspection, testing, and certification of pressure vessel operating at either internal or external pressure exceeding 15 psi. Section 8, Division 2 provides alternative or more stringent rules for the design, fabrication, inspection of vessels than those found in Division 1. Most pressure vessels for US refineries are now built to conform to the latest edition of Section 8, Division 1. Some high pressure vessels are designed and built in accordance with specification of Division 2, Section 8. Division 3 provides alternative rules for construction of high pressure vessels with design pressure generally above 10 ksi. Both Division 1 and Division 2 Section 8 of the ASME which require the manufacturer of the vessel to have a quality control system. Before the manufacturer can obtain a certificate of authorization from ASME, the written manual needs to be provided and the system implemented. The quality control system requires detailed documentation of examination, testing, design data regarding the vessel and provides a history of the construction of the vessel. That documentation can be useful when evaluating vessel in service. The ASME BPVC list material that may be used for construction, gives formula for calculating thickness, provides rules of methods of manufacture and specifies the procedure for testing completed vessels. Inspection is required during construction and testing of vessel. The code also prescribes the qualification of the person who performed the construction inspection. Spears, Horton's spheroids, noted. After a qualified construction inspector certified that vessel has been built and tested as required by ASME BPVC, the manufacturer is empowered to stamp the vessel with the appropriate symbol of the ASME BPVC. Some states and cities and many countries have laws other than requirements of ASME BPVC and other codes that govern the design, construction, testing, installation, inspection, and repair of pressure vessels used in their localities. The codes may be supersede the ASME PVC and their codes minimum requirements. Construction codes are periodically revised as the design of pressure vessels improve. Pressure vessels improve and as new construction materials become available, a refinery and petrochemical facility inspector should be familiar not only with the latest edition of build codes, but also with previous editions of the codes and with other specifications under which vessels they inspect were built. Inspectors should be familiar with any regulations including city, country, parish, provincial, process tower. Region for inspection. Okay friends, we'll stop here.